So, in the previous sections we have discussed about the conduction and convective heat transfers. So, there you have seen that both these modes of heat transfer, they require a medium and temperature difference, a finite temperature difference. Without that, the conductive or convective mode of heat transfer is not at all possible. Contrary to this, in radiative transport, we do not require any medium and neither any temperature difference, right. But that does not mean that in radiative transport that heat will flow from net heat will flow from low temperature to high temperature. It is not at all like the case. But what I am trying to point out that if I have two objects 1 and 2 and it has got a temperature T1 and T2, only radiative transport is possible, and it is the case where we have no medium, right. So, the point is one will transfer heat to 2, let us consider T1 is greater than T2, 2 will simultaneously also exchange or also deliver some heat to 1, right. However, E12 is higher than E21 and E net we can write E12 minus E21 to be positive. So, this indicates that 1 and 2 will simultaneously exchange the heat, which means that no temperature difference is required because T1 is at higher temperature than T2, right. But still 2 will deliver some amount of heat to 1. So, the point is here that E12 and E21 both are non-zero. However, E12 is greater than E21 and that is why there is a net heat transfer from high temperature object to the low temperature object, right. So, that is the striking difference of radiative transport in comparison to conductive or convective transport. Now, thermal radiation, you see thermal radiation is an electromagnetic wave, right, and like all other electromagnetic wave, it has got two properties. C will be equal to lambda into nu. C is the velocity of light, which is approximately equal to 3 into 10 to the power 8 meter per second. Lambda is the wavelength and nu is the frequency, right. So, and additionally we have the Planck hypothesis that energy of an electromagnetic radiation per quanta is equal to h into nu, where h is the Planck constant, which is a dynamic constant of a system, and its exact value is something 6.6256 into 10 to the power minus 34 joule second, right. But the point here what we want to emphasize that nu increases, E increases, right. So, we have higher penetrative power of this radiation as we have high frequency. So, definitely the wavelength actually decreases, right. So, the wavelength decreases. So, from here we can understand that as nu increases, E increases. So, penetrability of this specific radiation to any medium, that also increases. Just like because of that the X-ray can penetrate through the different biomaterials and all, but cannot penetrate this bone matrix, right. So, but still if you go for lower frequency like gamma ray or cosmic ray, it can penetrate through this, even this dense bone matrix. So, the penetrability actually increases. Penetrability increases where the frequency this must increase and subsequently the lambda will decrease. Okay. And the range of this optical radiation, if you understand that this entire optical radiation, if we think of this, it will be like it starts from, we can think of lambda axis, it starts from this cosmic ray, then we have gamma ray, here we have X-ray, then it is ultraviolet, then here over a small region we will have visible spectra, then infrared, we have infrared. After that we have this thermal radiation, and next from somewhere here we have microwave, TV, radio wave, etc. And the range of wavelength, you see it is not a fixed wavelength, there is a range. Like cosmic ray, it has got a range. If this is 4 into 10 to the power minus 7 micron, up to that, in this side we have cosmic ray. Now gamma ray starts from here to 1.4, this 1.4 into 10 to the power minus 4. Over this we have gamma ray. The X-ray is 10 to the power minus 5, still shorter somewhere here. So, gamma and X-ray has got some overlapping ranges. So, this is X-ray. So, here it is 10 to the power minus 5 and it goes up to 2 into 10 to the power minus 2. Now, UV is 1 into 10 to the power minus 2, again overlapping, right, up to 3.9 into 10 to the power minus 1. So, this is 1 into 10 to the power minus 2, then 3.9 into 10 to the power minus 1. Visible range is a narrow band which is 3.9 into 10 to the power minus 1 to basically 7.8 into 10 to the power minus 1. You do not have to remember this just for a basic understanding. Now, infrared starts from 7.8 into 10 to the power minus 1 and goes up to 10 to the power 3. Right. Now, thermal radiation, it's 1 into 10 to the power 1 into 10 to the power minus 1 and it goes to this 3.9 into 10 to the power minus 1. Right. So, this infrared and thermal radiation, they have got totally overlapping range, right. This is infrared is 7.8 and this is 1 into 10 to the power minus 1. So, 1 into 10 to the power minus 1 will be somewhere on this side, I think, yeah, 3.9 into 10 to the power minus 1. So, it will go to somewhere on this side. So, this is the entire range of thermal radiation. And after that we have this microwave, radar, TV, radio wave, etc., starting from 10 to the power 3 and going to 2 into 10 to the power 10, right. So, that is the more or less the overall spectrum of electromagnetic radiations. And we have to focus on this thermal radiation regime, which is after this infrared and going up to this microwave, TV, radio wave and radar wave, etc. So, see, if before going into the radiation, we have to understand that how a body will respond when it has got some incident radiation, it is receiving some incident radiation. Like if this is the object, it is receiving some incident radiation, flux E dot, right, and that will be in watt per meter square. A part of this radiation will be transmitted, E dot T, a part will be reflected and a part will be absorbed. So, E dot is equal to E dot R plus E dot A plus E dot T. See that total incident energy flux, if it is E dot, a part it is reflected, a part is absorbed and part will be transmitted. Now, you see that if I divide this entire equation by E dot, I will get E dot by E dot R by E dot, which is a fraction of energy flux reflected, then fraction of energy flux absorbed and fraction of energy flux transmitted, right. So, this is called reflectivity. This is absorptivity and this is transmissivity. So, we can write reflectivity plus absorptivity plus transmissivity equal to 1. And you see this reflection and absorption, mostly what we deal in reality are the opaque systems, right, where the transmissivity is 0. So, reflectivity and absorptivity is equal to 1, and you see that the visual appearance of color is actually an interplay of this reflectivity and absorptivity. Like if an object is absorbing all these VIBGYOR, all the different spectrum within the visible range, right, except the red light, and it reflects the red, it will appear red. Like if so, VIBGYOR is incident, that is a visible spectra reflecting only red, rest is absorbed. So, this will appear as a red object, right. If it reflects all the incident radiation within the visible range, it will be appearing as white, right. And on the other hand, if it absorbs all the incident radiation within the visible range, then it is called, or then it will appear black, okay. And that is the normal notion of different color what we see for different objects. Now, you see that if I extend this idea to introduce a theoretically reference or ideal object in relation to its behavior to incident radiation, like over this entire wavelength range, this is the visible range, right. So, over here, if we are restricting ourselves over this domain, if over here alpha visible, only for visible incident radiation, if alpha visible is 1, then it is black colored object, right. And if alpha visible is equal to 0, and everywhere tau is equal to 0, the transmissivity equal to 0. If alpha visible equal to 0, then it is white colored object. Now the idea specifically not of this white object but of the black object, if I extend over the entire scale of known wavelength, that over the entire wavelength now alpha is equal to 1, right, then it becomes a black body. An ideal object in terms of its behavior to incident radiation. Right. So over the entire wavelength range, that is from nearly 0 towards infinity, right. 0 means towards the cosmic ray, and still rays which we don't know but what we can theoretically think about of still lower wavelength. So means from 0 to infinity over this entire range of lambda, right. If over only the visible domain, we know that if all the incident VIBGOR spectra is being absorbed by this object, the body will appear black, but that is black colored object. But if we think of a theoretical object, right, ideal object, which absorbs all the incident radiation over the entire wavelength range, it becomes a black body, right. So black body is a theoretical object. It's an ideal object, just like equivalent to reversible process in thermodynamics. No process in reality is actually reversible. All processes are irreversible. But we introduce this reversibility such that we can perform some calculations of work and heat exchange, and from there we can actually gauge the behavior of actual process by introducing something called irreversible efficiency. Very similarly, the approach of science is something like that, that whatever we observe in reality with respect to certain properties, let's idealize it, go for a reference or a datum, right, and with respect generate some theoretical structure for that datum because it is easy to generate relatively, and with respect to that behavior you compare the behavior of real life objects introducing some empirical parameters. Just like in thermodynamics we can do it in terms of this irreversible efficiency, and here we will do it, we will see later that here we will do it in terms of something that is the absorptivity, where absorptivity of this black body is equal to 1, and also we will actually carry forward our analysis of this type with another parameter called emissivity. So we will discuss about it, right. So black body has got a defining property that alpha is equal to 1, right. Rho and tau will be equal to 0. Tau is definitely is equal to 0 because most of the objects are non-transparent or opaque. However, not in terms of its behavior towards any incident radiation, but also in terms of emission, the black body is another reference level. It has been established, or it can be theoretically established, that at a given temperature the emissive power of a black body is maximum. That is, the amount of energy it will release at a specific thermal state per unit time, per unit area is also maximum, right, relative to any other object. So black body has got some characteristic features. The first one, a black body, this is the defining equation or defining criteria. A black body completely absorbs the incident radiation irrespective of its wavelength. Over the entire wavelength it will absorb all the incident radiation and alpha will be equal to 1. And second characteristics, what I have mentioned just before, that black body is a perfect emitter. So at a given temperature it will emit maximally, right. At a given temperature it will emit maximally. No other surface can emit more radiation than a black body provided that they are at the same temperature. So, thermal state must be same. And another property which is very important, and we will actually explore that property, that radiative property or absorptive property of a black body is independent of direction, right. So, it is not a spectral object, it is rather a diffuse object, perfectly diffuse object. Like emission of a black body occurs in all possible directions, right, and also the absorptions. Like if I have an object, a black body, which is a black body, so its emission in this direction, or in this direction are all this, it has got the unique intensity in all directions. So, uniform intensity is in all directions, right. So, that is the emissive power of a black body, and similarly if there is some incident radiation and towards any other incident radiation or another angular incident radiation, its behavior towards any incident radiation will be independent of the direction of incident radiation with respect to some difference. So, these are the fundamental property of a black body. Now, as we are talking about the emissive potency of an object, let us formalize its definition. It is called emissive power, right. It is called emissive power. Now, you see that when we are talking about the emissive power, we may be interested that what is the emissive power over, or how the emissive power is dependent on lambda, because as we go on changing the wavelength, emissive power may change. The body is basically responsive towards a specific band of the spectrum, and it may not have the uniform distribution, right. And alternatively, we can think of the overall emissive power, that is over the entire range of wavelength from 0 to infinity. So, when we are talking about emissive power, there are two definitions. One is monochromatic emissive power, right. There is the amount of energy radiated or emitted, or rather, by the surface per unit time, per unit area, and per unit wavelength, right. Amount of energy emitted by a surface per unit time, per unit area, per unit wavelength. So, you see that we can write it as E lambda, and it is the amount of energy, say this is the energy per unit time, per unit area, per unit wavelength. So, here we will have a second order derivative or second order differential, right. So, alternative to that, we have total emissive power, and simply the same definition, amount of energy emitted by the surface per unit time per unit area, right. Per unit area is the total emissive power, which is E, and obviously it is dQ dA. So, you can understand from these two that E will be equal to 0 to infinity E lambda d lambda. E is equal to 0 to infinity E lambda d lambda. If I integrate, it is obvious from these two relations, right. If I integrate this monochromatic emissive power over the entire range of this wavelength from 0 to infinity, we must get the total emissive power. Now, as I have mentioned that actually for black body, this E lambda and E, these have been formalized long back using the idea of thermodynamics and quantum physics, right. In 1900, Max Planck introduced the expression of, we will not go for the proof because it is beyond the scope of EB lambda, that is the monochromatic emissive power of a black body, right. Theoretically, it has been calculated, and in order to do so, he actually introduced the hypothesis that energy is being released by the system in the form of quanta, right, and each quanta, its energy is proportional to the respective frequency. Okay. And there were a lot of these other assumptions like these emitters there are simple harmonic oscillators. So, they, as they move, actually they will radiate energy. Why? Because whenever in any object, like think of this filament in an electric bulb. So, we have the metals like tungsten and all, it is some metal. So, they are packed in a regular fashions and possess a unique electric and magnetic dipole. So, if I am increasing the energy, right, I am increasing the energy or increasing the temperature rather here, temperature of the filament upon passing current, at a point what will happen? The vibration frequency and amplitude will be such that they will generate the electromagnetic wave with a wavelength within the visible range. So, it is actually appearing to be visible or incandescent over this visible range. So, we are not going into the theoretical part of this Planck's derivation, but what we have to understand more qualitatively, we can see that what is happening, that every metal or metal this positive metal ion in a metal bond in this bulb filament is acting as a simple harmonic oscillators, and when we increase the temperature, it releases an electromagnetic wave, right. And for a specific temperature, right, for a specific current value, and definitely it has got a unique resistance, it becomes incandescent. So, what is the final expression? The expression is, you see that EB lambda has been expressed as 2 pi hc square into lambda to the power minus 5 divided by exponential of hc by lambda kt minus 1, right. So, yeah. So, here you see that we have two variables, or rather temperature is functioning as a parameter, whereas lambda is a specific variable with which EB lambda drastically changes. So, it will give you a distribution, right. It will give you a distribution of EB lambda with respect to lambda at given temperature. So, it behaves like this. Like this, and this is temperature, lowest temperature T1, T2, T3 and T4, and this is the scale of lambda, this is EB lambda, and you see that T4 is greater than T3, greater than T2, greater than T1. So, what we observe that it achieves a maxima as we go on increasing lambda from 0, right. We go on increasing the lambda from 0, it passes through a maxima and then again decays down. So, there is a region of lambda where EV lambda achieves its maximum value. And what we further observe, without going into this expression, that with the increase of temperature, the lambda at which this is say lambda max 4, this is lambda max 3, lambda max 2 and lambda max 1, right. So, with the increase of temperature, lambda max actually decreases, and we can think of a locus like this. Okay. There is a locus like this, and with which the lambda max shifts to progressively lower values with the increase of temperature. So, here you see that we can locate this point of maxima of EV lambda if I simply take the derivative of this expression. So, what I am talking about, d EV lambda d lambda, if I solve, what I will get? 2 pi h c squared into minus 5 into lambda to the power minus 6, right? Into e to the power h c divided by lambda k t minus 1 minus this 2 pi h c square into lambda to the power minus 5, and then denominator, so it will be e to the power h c by lambda k t minus 1 square into e to the power h c by lambda k t into this h c divided by we are taking the derivative with respect to lambda, so minus lambda square this k into t, right. So, what do we have? That this is equal to 0, this is equal to 0. So, we drop this term and this term, and also lambda to the power minus 5. So, here it becomes lambda to the power minus 1, right. So, and lambda to the power minus 1 means here. So, this is also cancelling out with it, and 2 pi h c squared, 2 pi h c squared is going out. So, minus 5 divided by, or minus 5 plus everything else cancels out, into e to the power h c by lambda k t into this minus of h c divided by lambda k t, that divided by e to the power h c by lambda k t minus 1 equal to 0, right. So, something like this, and this minus and this minus cancels out also. So, on an average this will be the equation, right. There may be some this error in sign, I do not know, I am doing it for the first time, I have not checked it out, the exact expression, whatever it is, that is not important. What is important to note, that we are not going to actually solve it, that this is a functional form of lambda into t, and that is equal to 0, and this is a transcendental equation. We have seen that this transcendental equation can be solved actually upon using some Newton-Raphson kind of method, and we will get what? The solution will be this, and this lambda will be definitely lambda max. So, lambda max into t equal to some constant, right. And if I solve it out, I will get, because finally it is numerical solution, lambda max into t equal to 2898 micron Kelvin. And this equation that lambda max, that EB lambda will achieve the maxima at a specific value of this lambda, and this will go on with changing temperature. This has been proposed by Wien much prior to Planck's theory, right, using thermodynamics, and this is called Wien's displacement law. Wien's displacement law. Right. Just like if I think tentatively that sun is a black body, then definitely it is not, but it will give you more or less a correct answer. See that the sun average temperature is, surface temperature is 6000 Kelvin. So lambda max is close to 0.3 micron. So it gives you that sun will emit its maximum radiation over the visible range, which is actually true, right? Which is actually true. It emits its maximum radiation in the visible range. Definitely there is a wide fraction in this ultraviolet and also in the infrared range, but majorly it emits in the visible range. So that we can directly conclude from Wien's displacement law. And you see, this Wien's displacement law is useful in explaining the color of an object, hot object, as we go on increasing the temperature, at least over the visible range. What is that? See that in a dark room, if I think I have a metal object which has got infinite melting point, theoretically. So now if I start heating it from room temperature, in room temperature it's practically emitting nothing, right? So as we go on heating, first if the room is evacuated, let's say, first we will feel the heat, and which means that it's emitting radiation in the thermal radiation range. Next, still we can't see anything. Next it will emit some infrared maybe, and some visible, some thermal radiation at the same time, right? So you see that if I think that this is the wavelength range and this is the narrow visible range, okay. So initially it's emitting something like this, so you can't see it. Next, as we go on increasing the temperature, it will emit something like this, and the body, say in the VibGeo, this is the red band, so it will appear red hot, right? It will appear red hot, and after that, if you still go on increasing the temperature, it will be like this, it will appear red plus orange, and after that, if you still go on increasing the temperature, it is appearing, it's emitting red, it's emitting orange, and all the other spectrum as well. So if it is something like this, over this region, it will be white hot, right? So for this, it is red hot, and finally it will white hot, and maybe it's covering the entire visible range, right? This is the visible range. So this is the theory of color of a hot object as it appears with changing temperature. However, definitely it is not as smooth as a black body, because actually nothing is black, so it will be not smooth and not having this this smooth profile. It may be to some extent distorted compared to this. However, the overall pattern of emission will be like this, okay. So that's about the Wien's displacement law and associated explanation of different colors of hot object. So next we will think in terms of its emissive property of a non-black surface, right, and how we can rate that emissive power relative to a black object or black body, right. So, this is called the Karshaf's law. So, in Karshaf's law, what is being stated? You try to understand. We have, say, a large black enclosure. This is a large black enclosure such that any object placed here will receive a flux Q or radiative flux Q it will receive, right. And let us consider a body 1 which has got surface area A1, right, and it will also emit its monochromatic emissive power is E1, so it will emit E1 A1 and it is absorbing, or rather it's being hit by a radiative energy flow rate A into or A1 into Q, right. Now, out of this incident A1 into Q amount of radiation, only a fraction which is alpha, that is the absorptivity, will be absorbed by this object, right. So, incident energy flow rate is Q into A1. Next, absorbed energy or rate of energy absorption alpha into Q into A1. Rate of emission E1 into A1, right. So, under thermal equilibrium, we have alpha into Q into A1 is equal to E1 into A1. So, E1 is equal to alpha into Q, right. Let body 1 is black, think about it. So, alpha is equal to 1. So, E1 or EB rather will be equal to Q, okay. EB is the total emissive power of a black body. So, that EB is equal to Q, and immediately what we will have, we define emissivity of a non-black object as epsilon is equal to E divided by EB, right, E divided by EB. So, obviously we can say that if EB equal to Q, then E1 is equal to alpha into EB, and E1 by EB is equal to alpha, which means epsilon is equal to alpha. So, absorptivity and emissivity are same for any object under thermal equilibrium. So, what is the final statement of Karshaf's law? Under thermal equilibrium, alpha is equal to epsilon. So, strictly this equation, though under strict theoretical constraint, we should apply this equation only under the condition of thermal equilibrium, but you see this alpha is less dependent on the temperature or wavelength, same as epsilon. This alpha is specifically least dependent on temperature. So, even if the object is not in thermal equilibrium, still the Karshaf's law in most of the cases remain valid, but within the theoretical paradigm and within the stricture of the theoretical paradigm, we cannot use this Karshaf's law when the body is in thermal transience. Okay. So, you see it, I have mentioned it in the handout that The absorptivity of most real surfaces is relatively insensitive to temperature and wavelength. So, for practical purpose, it is customary to assume that emissivity and absorptivity of a surface are equal even when it is not in thermal equilibrium with the surrounding. But if it is necessary for a rough theoretical or approximate theoretical estimate, we can use the Karshaf's law, right, even whenever the body is passing through some radiative transients. So, one thing I have missed, that regarding the total emissive power, the law which you have studied from your school days, that is the Stefan Boltzmann's law, right. Stefan Boltzmann law, and which states that total emissive power of a black body is proportional to the fourth power of temperature. So, actually you see that EB we know, this is basically this EB lambda into d lambda 0 to infinity. So, EB lambda, if I substitute 2 pi h c square inside, or rather we can write that 0 to infinity k1 into lambda to the power minus 5 divided by e to the power k2 by lambda t minus 1 d lambda, right. So, the thing is, this term, this entire term, this k2 by lambda t, that we have to expand in inverse binomial series, and whenever I will expand this, right, like if I write it as e to the power minus k2 by lambda t to the power minus 1, I will have 1 plus e to the power k2 by lambda t plus e to the power k2 by lambda t square, right, and so on and so forth. Sorry, not square, it is 2, because 1 plus x square x is this. So, 1 plus x square is the expansion of 1 minus x to the power minus 1. So, I will go on writing this, and for each term I have lambda to the power minus 5, right. So, it will be for each term in this infinite series, it will be a kind of gamma function. So, it will be an infinite sum of gamma function, where from we can actually get this form. Though the exact the sigma value, the constant value as predicted by Planck and as proposed by Stefan Boltzmann's law, they are slightly different. According to Stefan Boltzmann law, it is 5.67 or something. 5.67 into 10 to the power minus 9 watt per meter square Kelvin to the power 4. Whereas from Planck's theory, it has been proposed that this 5.729 into 10 to the power minus this 8, sorry, here it is 8 watt per meter square Kelvin to the power 4. There is a slight difference, right. So, that is all about the theories of black body and idea of this non-black objects emissivity. We have a new parameter we have introduced in the Karshaf's law, by which we can rate the performance of a non-black object in terms of its emissive potency with respect to a black object. Now, in addition to that, to idealize the object, that is, one is black, another is white. White body is not that important. This idealization is not that important in radiative transport of heat, at least this whatever the chemical engineering processes are concerned. We are not actually use this idea of heat body to white body that much, but instead we use another semi-ideal object which is called gray body. So, what is gray body? See, we have defined epsilon as total emissive power of a non-black object divided by total emissive power of a black object at the same temperature. So, extending this idea of emissivity, or rather this is called total emissivity, we can extend this idea to monochromatic emissivity as well. So, where epsilon lambda will be equal to monochromatic emissive power to that of black body term. So, this is monochromatic emissivity, right. If let us formally introduce this definition and next we will explain. If monochromatic emissivity is independent of lambda, then it is a gray body, right. So, what will happen actually? See, E lambda by lambda. So, this is the large enveloping curve, this is a black body, EB lambda, right. And if I think of another curve which is proportionally changing such that at each and every point the ratio remains the same, like here this is E lambda, this is EB lambda, or for any other point the ratio of E lambda and EB lambda remains the same. So, this is a scaled down version of this black body's curve. So, this is gray body, right. And we can think of a real surface which is a non-black, non-gray surface like this, where there is no pattern. So, this is non-black, non-gray surface. So, that is the understanding. So, gray body at least we will use this idea because many industrial surface can be well approximated by diffuse gray surface. Diffuse means where there is no spectral preference of emission, right. We will discuss it. So, that type of surface we will call a gray surface, and with respect to that we have defined a gray body and the respective monochromatic emissivity term, right. So, in this next session, actually we are going to discuss now the special property of radiation. Once a surface is emitting radiation, right, if I have a emitting surface, once a surface is emitting radiation, definitely the radiative flux in this direction will be lower than the radiative flux here. So, there is some property which is called intensity, right. So, this intensity actually will vary as we change the direction of preference. Here if we choose this specific direction, we will have a different intensity compared to this specific direction, right. However, we have to limit our discussion of intensity, or the mathematical analysis we have to limit only in case of black body. Why? Because if a body has got inherent preference of radiation in a specific direction because of its surface morphology, right. It has got, it tends to radiate more in a specific direction, right. Then we cannot do a mathematical analysis because that corresponding intensity distribution itself is totally subjective. It varies from one object to another object. So, we will, in discussing what is intensity, and definitely whenever we are talking about the emissive property, there will be something called spectral intensity and total intensity, right. So, considering the overall basis of black body, in the next session we are going to elaborate on the spectral and total intensity, and we will also see that how the spectral and total intensity of a black body are related to its monochromatic and total emissive power. So, we will continue with our discussion in the next session. Thank you.